Okay, so we're going to do a real brief introduction to area and polar coordinates, okay? I'm going to go through this very quickly because it's really, I don't know if it's going to really help you remember the formula for area for polar, but we're going to start with the area of a circle. Okay, formula for area of a circle is pi r squared. Okay, and the whole idea of this is that a piece of a polar curve looks like a piece or a sector of a circle. Okay, a sector of a circle. If you remember back to geometry class, the area of a sector with central angle theta, what did you do? Well, you figured out what part of the circle you had. And the part of the circle that you have is your theta angle in radians divided by 2 pi. All right, because 2 pi is the angle that takes you all the way around the circle. So you take whatever theta angle is your central angle, right? Central angle being right in there. That's your theta. Okay, and you multiply it by your pi r squared. Okay, and what happens there is that our pi's divide out, and we end up with our 1/2. I'm going to rearrange my terms a little. So I have a 1 over 2, I have an r squared, and I have a theta. Okay, and just in the interest of this video, keeping it nice and short and concise, I'm just going to skip right to this and just tell you that our angle thetas are going to be our sections of our polar curve. So we're going to carve out sections of our polar curve, and every section is going to have a central angle, and that central angle we're going to call delta theta. Okay, so when I use this formula, I will in fact have a 1/2 r squared delta theta. Okay, and if I add up, right, this is going to be for one little sector of my circle, or one little section of my polar curve, whatever that polar curve looks like. And what I'm going to do is I'm going to add on the area of each little section, one at a time, which is going to give me a summation. And if I take infinitely many of these, I'm going to end up with an integral. Okay, so the area of a polar curve is going to be given by 1/2 the integral of r squared d theta. Okay, and I'm going to start from theta equals a to theta equals b. Okay, so a very, very crude derivation of the formula, but the 1/2 r squared theta comes from our area of a sector of a circle. Okay, we don't have circles, but if we take tiny, tiny little pieces, they behave like circles, and that's why this formula works. But, you can just memorize the formula. So this is what we're working with. So if we want the area on a polar curve, it's 1/2 the integral from a to b of r squared d theta. The big thing on polar curves is to figure out what your a and your b values are, okay, to figure out where your region starts and where it ends in terms of angles of theta. Let's look at some examples. Okay, so I want to find the area enclosed by one loop of the four-leafed rose curve, r equals cosine 2 theta. Okay, so first of all, let's look at what that graph looks like. That's the one that we graphed together. Okay, and this is where graphing this kind of comes into play. I want to set up an integral that is going to give me the area inside one petal, or one loop of the four-leafed rose. So now my basic formula is going to be area is 1/2 the integral of r squared d theta. Okay, so I'm going to be doing 1/2 the integral of cosine 2 theta quantity squared, or cosine squared 2 theta d theta. Okay, that part is the easy part. The difficult part is figuring out what the bounds should be. Okay, I got to go from a to b. I got to figure out where I should integrate from and to in order to get one loop. There's actually a bunch of different ways that I can do this. Okay, there's actually infinitely many ways that I can set up the bounds on this integral. I want you to pause the video and try to come up with maybe two different bounds that would work, two different sets of bounds that would work to get you the area of one loop. So pause it and come back to me when you're done. Okay, so there's a lot of solutions to the problems of these bounds. Okay, I could go from 0 to 2 pi. Okay, but how many leaves is that going to give me? How many petals will that give me? Well, that's going to take me all the way through the rose curve, so that'll get me 4 petals. So how do I get just one petal's area? Well, I divide this by 4, or do 1/4 times 1/2 the integral from 0 to 2 pi of cosine squared 2 theta d theta. That's one option. Okay. If I think about how this rose curve is carved out, if I start at theta equals 0, I'm here, okay, and I carve out my area this way, and I'm in there at, okay, and the question is, okay, so if you guys can answer the question of when I come back into the pole to get that top half of that, this part of the petal, that's my first time that r is equal to 0, so you can go back to how we graph. So you can go back to when we graphed it and think about that first time that you hit the theta axis, or you can think about where is cosine 2 theta equal to 0, and cosine 2 theta equals 0 when theta equals pi over 4. So I could do an integral from 0 to pi over 4, but how much of my petal does that get me? It only gets me half a petal, so how do I fix that? I can double this integral. Okay, that's another solution. Okay, I also could have thought about one hump of my sine curve, my cosine curve. Okay, or actually, I guess it would be going from, if I went until pi over 2, that would take me through there and then down through here, and that would be the area from 0 to pi over 2. That also gets me to one petal of my rose curve. Okay, so if I integrate from 0 to pi over 2, it's half of one petal and half of another petal, but it adds up to a whole petal's area. So that's another solution. If I wanted to focus on how to get a single petal, okay, both sides of the same petal, I could have gone from where this petal is begin, which is at pi over 4. I start down through here, and I finish it up at 3 pi over 4. I sweep out the rest of that area. So I could have done an integral from pi over 4 to 3 pi over 4. Okay, and that would have gotten me through a solid petal. Okay. In the same vein, my next petal happens from 3 pi over 4 to 5 pi over 4, which would be this petal. So I could have gone for that petal and gone from 3 pi over 4 to 5 pi over 4. And that would have given me a full area. Okay. One of the ones that I like to use a lot is to focus on our first petal and to carve it out kind of backwards. So to get this area in here. Okay, and one way to do that, I have two ways to do that. First petal, I can go from a negative pi over 4, and you guys probably can't read that, to a positive pi over 4, and that would get me that would give me that first petal on the right side of the x-axis, because negative pi over 4 is going to take me back before I start, where we started graphing it the other day, but it will get me to the same area. And in the same vein as this, I can also do, well, on second thought, I'm just going to stop there. Okay, there's 6 different options to get you the same area enclosed by one loop of our rose curve. And the easy part is doing 1/2 r squared. The hard part is figuring out what those bounds should be, okay, and that's where the difficulty lies. So on Friday we're going to be doing just inside a single rose curve, or not necessarily rose curve, but a single polar curve, and then on Monday we're going to be bringing in 2 rose curves. 2 polar curves. I'm looking for areas, either common areas or areas between 2 polar curves. But that's it for Friday. So I almost forgot, but this is kind of a funny integral to integrate if you're asked to integrate this by hand. So I just picked one of the choices that we had from the last slide, and I like this one because the bounds are going to be easy to plug in. It's going to be real easy to evaluate a trig function at both 0 and 2 pi, versus if I plug in pi over 4 and 3 pi over 4, it's going to take a little bit more thought. Some of the other options that were good were the integrals that we had from 0 to pi over 2, or we could have even written an integral from 0 to pi, and that would have been a nice, but pick an integral that has nice bounds if you're going to be integrating by hand. Okay, so first of all, let me just simplify that coefficient, and now we can talk about why this integral is a little funny. Okay, so if I look at this integral of cosine squared 2 theta d theta, hopefully you recognize that cosine squared 2 theta is a composite function. Okay, if I try to pick a u of, let's say, 2 theta, and I have my du as 2 d theta, I will have an integral of 1/2 the integral, of cosine squared u. And so what's the antiderivative of cosine squared u? You can pause and think about it if you need to. The answer is, I don't know. Okay, cosine squared u is still a composite function. I don't have a function whose derivative is cosine squared. So there's nothing I can do with this, so this doesn't work. Okay, if I were to pick a bigger u, what would that u be? Well, I guess u could be cosine 2 theta. And if u is cosine 2 theta, then my du will have a sine in it. And that won't work because I have no sines in my problem. Okay, so none of that stuff works. So I need something better, okay? And that better thing is one of those wonderful, wonderful, wonderful formulas from pre-calc. It's sometimes called a power-reducing formula. I've seen it called other things as well. But the two formulas from pre-calc that we're going to be utilizing here are, okay, so these formulas from pre-calc: cosine squared x equals 1/2 times 1 plus cosine 2x, and sine squared x is 1/2 times 1 minus cosine 2x. The reason that these formulas are great in this situation, these power-reducing formulas, is that it takes us from a composite that I can't u-sub with a trig term squared, and it takes me to a composite that I can u-sub out my way out of with that cosine 2x. It's a simple, a more linear composite with that, just a plain old cosine instead of a cosine squared. Okay, so these two formulas we're going to have to memorize. The silver lining is that you'd have to memorize them when we go back to Chapter 7 to learn those other integration techniques anyway. So you're going to need them, so might as well learn them now. But I'm going to make that substitution. Now, if I have cosine squared x being 1/2 times 1 plus cosine 2x, what do you think I'm going to have when I have cosine squared 2 theta? So think about that. Try to rewrite your integral and pause it and come back to me when you have your new integral. And you should have come up with 1/8 times the integral from 0 to 2 pi of my cosine squared 2 theta becomes a 1/2 times 1 plus cosine 4 theta d theta. Okay, so the angle is doubled when you do a power reducing formula. Okay, so now this is still a composite function, so I'm still going to do a u-sub. So I'd have u as my 4 theta, the inside of that trig composite, and then du would be 4 d theta, which means I'm going to have a coefficient of 1/4 out front. So if I combine the 1/8 and the 1/2, multiply them together, I'll have, well, you simplify this with your u-sub. I'm going to ignore bounds for a second, so let's do this without bounds, and we'll come back and put our bounds in. Okay, so making that u substitution, I pulled out that 1/8 and the 1/2, and I have my 1/16. Okay, my 1 plus cosine 4 theta, when u is 4 theta, becomes a 1 plus cosine u, and my d theta is going to become a 1/4 du. Okay, so again, if you need to finish up your integral, you can pause it and you can come back, but I'm going to have my coefficients combine to be 1/64, and my antiderivative of 1 du is u. The antiderivative of cosine u is plus sine u. All right, and I'm going to plug back in. So again, if you need to pause, go ahead and do it. Okay, but I'm going to plug back in for u as 4 theta, and I will have 1/64 times 4 theta plus sine 4 theta. Okay, and I'm going to bring my bounds back. I'm going to go from 0 to 2 pi. All right, so I'm going to do upper bound minus lower bound. If you need to pause to do it, go ahead and do that, and come back to me when you've evaluated this. Okay, so I'll have 1/64 times upper bound 4 times 2 pi is 8 pi, plus sine of 4 times 2 pi is sine of 8 pi, minus 0 minus sine of 0, and sine of 8 pi is just 0, and sine of 0 is just 0. So I have 1/64 times 8 pi, or pi over 8. Okay. Okay, so again, anytime you have a cosine squared or a sine squared, you're going to have to use these lovely power-reducing formulas, okay, and that'll get you through it, okay. They're going to require u-subs still in your integrals. You can hold the bounds, you can not hold the bounds, you can do the u-sub in your head as long as you're getting the answer right. You don't need to show me the full u-sub. Okay, so there actually is the entire lesson.